We have made improvements to the GUI of our CNC control application. The interface is now separated into two distinct windows for improved usability. Firstly, our main CNC control window for CNC execution, as well as our settings window for configuring hardware-specific parameters. This separation ensures that users can configure settings such as microsnapping or pin assignments without cluttering the main operational view. Once configuration is complete, the settings window can be closed, keeping the interface clean and focused on active tasks. One key feature in our settings window is pin assignment validation for microsnapping control pins, MS1, MS2, and MS3. Each pin selection is mutually exclusive, meaning once a pin like pin 45 is assigned, it cannot be reselected for MS2 or MS3. This safeguards the user from accidental misconfigurations. Additionally, we use a local configuration file to store user settings across sessions. Setting this to 39, it still retains as 39. This file stores critical parameters like selected pin, step angle, and microsnapping values used in the calculation of movement. If the config file is deleted, the system automatically regenerates it with default values. Our CNC workflow remains largely the same. The process begins with connecting to microcontroller, followed by loading a G-code file that represents the desired toolpath for execution. As in, our new feature is G-code visualization. G-code files, especially complex ones, are not easily readable or interpreted by humans. To address this, we pass the coordinate data within the G-code and generate a 2D representation of the toolpath. In this example, we've loaded a simple G-code file with only a few linear moves. The plotted toolpath clearly shows the path the machine will follow. For more complex paths, visualization becomes even more valuable, allowing users to verify paths before execution. Implemented manual control and location retention features. Users can manually move the tool using both absolute and relative positioning. For example, we can move the machine to absolute coordinates of 0, 0, 0, followed by setting it as our home position. From that home, issuing a relative move of 50, 0, 0, will move it to the expected location of 50, 0, 0 as shown. The system can return home with a single command. This flexibility allows for more intuitive job control and helps ensure position when aligning the workpiece. For firmware improvements, our first feature is the bare metal implementation of several functions. We transition from Arduino's standard wrapper functions to a bare metal approach, allowing for greater speed and reduced overhead. For instance, we replace wrapper functions such as pin mode and digital write with direct manipulation of the data direction registers and port output registers. This change eliminates the latency introduced by abstraction layers, allowing us to drive stepper motors at higher frequencies. We've also redone our end stop and emergent stop logic. Previously, our system relied on a polling-based method, which continuously checks for input state changes in the main loop. This approach consumes more CPU cycles and can delay response times, as well as increasing memory usage. Now, we use hardware interrupts. This provides instantaneous reaction to events such as emergency stops or end stops being triggered. As a result, this results in low memory footprint and faster input handling, and most importantly, more reliable safety features which are critical for CNC applications in the case of our hobbyists.